All right, what do I have first? All right, so this is a classic example. If you watch the videos, this should be very straightforward. So can anybody have a crack at it? A, B, or C? Yeah, Christy, that's right. B is correct. It's pretty obvious answer choices, but to walk through it, we know that from chapter 3, if it doesn't tell you otherwise, you're assuming that the reaction is occurring in an aqueous solution, and so this metal kind of dissolves away, and therefore your nucleophile really is just this cyanide ion. And so this is your nucleophile. This is your substrate. So can somebody tell me what classification of substrate this is? Primary, secondary, or tertiary? Primary. And what kind of reaction prefers a primary substrate, Sn1 or Sn2? Yeah, Sn2. So for Sn2, it goes methyl. This is in the order of reactivity. Methyl, primary, secondary, and tertiary. This is worst. This is the best. I mean, well, my mistake. Sn2. This is for Sn2 order of reactivity. This is the best. This is the worst. The tertiary is like never going to happen. But we know that this is a primary. So Sn2, it all happens in one step. So this Br is going to leave. This is now our base endonucleophile. So this is going to attack. And we have Cn, and B is our product. Everybody get that? Makes sense? So, and in terms of reactivity, Sn1 is the complete opposite. Sn1 prefers tertiary, secondary, and primary. Next up, no problem. Next up, what is the leaving group? Does anybody, so I've seen this problem show up in bonding. I kind of don't understand why people get it wrong because it's really a fundamental thing, what's leaving in the reaction. So does anybody know which one is the leaving group? You're given this whole reaction out of all these 4 choices, which one the leaving group is? Anybody know? Bueller? No. So, Christy, it is not A, and so let me walk through it right now. So here, we have an alcohol. Here we have, I like to, if there's a charge on it, I like to draw it out. So these two are going to react together. What is the substrate? The alcohol or this thing here? Actually, this thing here is the substrate. Remember, the things that have extra lone pairs are going to be what's doing the attacking. So this alcohol actually has lone pairs to use, attack, and bond with, while this only has one lone pair because it has that extra bond to it. And as a rule of thumb, I'm just going to say right now, I'm just going to give the answer away, water is a very good leaving group. So this is going to attack this water, this is going to leave, and therefore your product is that. So for just making up an example, water, if you have water, if you have an oxygen that is positively charged, that means it has extra bonds to it that are making it beyond neutral. Therefore, it doesn't want that positive charge. Anything in electronegative doesn't want a positive charge. So in order to get rid of it, it's going to break away. All right, so water, if you have water, this is water, your H2O. If you have water on a substrate, on a straight chain or anything else, water is always going to want to leave. Does everybody get that? So therefore, in this reaction, the leaving group is water. And if you're given the whole entire thing, just look for what is left over. Kind of acids and bases where you can almost look at the products to see which one of the reactants was your acid and base. Here we have H2O in the reaction. That isn't present in this product. It's just floating around as this. So hopefully between this breakdown and this shortcut made sense. If anybody has a question about that, feel free to ask. Moving along, this was a quiz question in a previous semester. So, do Sn1 reactions have more than one product or only one product? Similarly, do Sn2 reactions have only one product or more than one? Does anybody know? So Sn1 reactions will have more than one product because Sn1, it's a two-step process, and so you have an alpha carbon. It's a two-step process. It's not all happening at the same time, and because it's planar, you can attack it from the back or you can attack it from the front. Therefore, you have a product that's R and you have another product that's S. Sn2, it's only attacking from the back. So what was wedged? If you're attacking from back, your new product will have the opposite stereochemistry, and it's only one product. So in Sn2, you only have one product. In Sn1, you have both RNS. So with this one, let's break it down. So we have this BR here is our leaving group. What classification of leaving group is this? Is it primary, secondary, or tertiary? Tertiary. And so we have a tertiary substrate. Therefore, we don't even have to look at the nucleophile. What kind of reaction Sn1 or Sn2 prefers a tertiary substrate? Sn1. And so from my rationale of this, will we have one of these or will we have both? Both is right. And going back to chapter 5, does anybody remember what we call an equal mixture of something? If you have one product and you have an equal amount of the other, a 50-50 mixture? Yep, Dylan, you're right, racemic. So another way he could ask this is what product which reaction. He could give you a multiple choice question. Which reaction will give you different reactions? Which one will produce a racemic mixture? And you therefore just check which one is an Sn1 reaction, and that will be your one that produces your racemic mixture. Moving. So Sn1 spec. Christy, that's correct. So hopefully you guys can see this. Okay. Rate law. I see this very common. Apologies, my mom's I swear one day I'm going to snap on that. So what is the rate law? So if you guys have gotten to the first page in your SI, you should know that Sn1 for your rate law, does it depend only on your substrate, or does it depend on your nucleophile and your substrate? Does anybody know? For Sn1, does it depend on only your substrate or both? Only the substrate. So we also know that Sn1 is first order. And so if you count up, you're going to see it in multiple choice fashion. So if you count up your bracket, if you count up your superscripts, if you count these up, it'll give you the order. So we shouldn't have any answer ever that has a 2 as a superscript, because 2 plus 1 is 3, and we don't have trimolecular reactions in this. So this example here, I'm just going to say R for the straight chain. Our rate of reaction should be R BR Why? Because this, Leah, do you have a question? You hit that raise your hand button. All right, we'll keep moving. So this, if you draw it out, will be like that. So what is this? This is a secondary. So this is secondary, and this, anything with a negative charge is strong. And so with a strong nucleophile, secondary and a strong nucleophile, you have a SN2 reaction. And SN2 we know is bimolecular. So 1 and 1, SN2 relies both on the substrate and the nucleophile, which is why we get this as our answer for that example there. Does that make sense, everybody? Going along to the other example, we have a tertiary. So just to draw this out, so we have a tertiary and we have a strong nucleophile. So what kind of reaction is going to occur? We said before, what kind of reaction, SN1 or SN2, prefers tertiary substrates? SN1, and SN1, when it comes to rate law, only relies on the substrate. So therefore, the rate law for this will be only the substrate. Christy, you're correct. SN1 has prefers weak nucleophiles, but first and foremost, you want to look at your substrate. So in order, when you're trying to figure out what kind of reaction, you go, what kind of substrate for primary, secondary, tertiary? If it's secondary, then you look at the strength of the nucleophile. That you could figure out almost every time what kind of reaction you get from there. And if anything, then you look at the solvent. So hopefully that rate law question makes sense. And speaking of solvent, polar aprotic and polar protic. So does anybody know what protic and aprotic means? It's fine if not. It's kind of the last thing you have to worry about. So polar protic protic means proton, and if it's able to donate that proton, you're also saying that that there's hydrogen bonding. So protic has H bonding, hydrogen bonding. Aprotic does not have hydrogen bonding. Does that make sense, everybody? And so when we talk about hydrogen bonding, what do you need to have for hydrogen bonding? You have something electronegative with an H. So if you have an H bonded to a carbon or a nitrogen, these are not electronegative enough to have hydrogen bonding. Does that make sense? And so we should be able to answer this question based on that information. So we're looking at polar aprotic, but what isn't polar aprotic? So we're saying what doesn't not have hydrogen bonding. Kind of confusing, but this is a example that I've seen in bonding before, so I don't want you guys to miss points. So what it's pretty much asking is which one is protic, right? If it's not polar aprotic, then you're asking for which one is protic. So does anybody know? Let's just say this is A, B, C, D, E. Does anybody know which one is protic? The alcohol. The alcohol is correct. That is your answer. Because here, this S and this sulfur and oxygen, although it's polar, you don't have any hydrogen bonding. So this one is aprotic. Here again, this nitrogen is attached to carbons. This oxygen doesn't have hydrogens, and so there's no hydrogen bonding occurring in this. This is aprotic. This is just a ketone. There's no hydrogens attached to something electronegative, so it's aprotic. And again, with the same thing here. So hopefully that made sense, because I've seen that show up on bonding, and I don't want to miss it. Moving along, you guys should know that Sn1 and Sn2 reactions occur at chiral carbons. So chiral carbons also have a 3D structure. So we know that this Br is our leaving group. So which type of reaction, if any, will be occurring? Does anybody think they know? I don't know how you'd be able to tell on a chair, Krista says. So in a chair, are you able to rotate? Are you able to flip stereochemistry on this bridgehead? No. So in this molecule, in this chair, this carbon is stuck in that conformation, whatever conformation that is in. It is stuck, it's rigid, it cannot move. And so it's not able to undergo a substitution reaction. So your answer is neither. I've seen this on what was it, bonding, but it was a extra credit question. Some people got it wrong, but that's the rationale behind it. That carbon isn't able to bend, it's not able to undergo any kind of flipping. And so if you're not able to undergo flipping, if something were to attack it like Sn1, we know that you have both R and S products. But if you're not able to do it in the first place, you're not going to have that kind of substitution reaction. So if you have this kind of question, if you have your leaving group on this bridge carbon here, same thing with this bridge carbon, in Sn1 and Sn2 reaction won't occur. Did everybody get that? And last but not least, I've seen this. The only reason why this is actually an Orgo 2 type question, but the only reason why I bring it up is because I've seen it on extra credit. So the trick to this is it doesn't undergo substitution right away. It undergoes an acid and base reaction with this NaH here. So we know that the metal is going to dissolve away, right? So this is our new reaction. And so we know from acids and base chemistry, this negative charge will want to fulfill itself. And so how's it going to do that? It wants a proton. Where is it going to get a proton from? The OH. So it's going to steal hydrogen from the OH. The bond from the OH is going to come onto itself. So therefore, we have this. And now you have this reactant with this, but this isn't gonna react. This hydrogen gas is neutral. It doesn't want anything to do with anything else, and so therefore, this actually is gonna react within itself. This is going to act as a base for this own reaction. And so we're going to see that this leaving group is going to leave. It's electronegative and big. It's a very good leaving group. And so just breaking it down with this, the leaving group leaves. And now this one of these lone pairs is going to go and try to fulfill that positive charge and bond with it. It's going to bond there. And so therefore, that is our new product. Does everybody see how I did that? Or does somebody have need me to walk through it again? Yeah, so again, the first step is acid-base chemistry. This Na is going to dissolve away because otherwise, because unless stated otherwise, it's occurring in the aqueous solution. So the metals on the first, in the first column, like sodium, magnesium, those are going to dissolve away. So you're left with this H negative with a lone pair. This H negative needs to fulfill itself and it wants a proton. Where is it going to get that proton from? The alcohol. It's going to steal that H from the alcohol. Therefore, you're left with this here. This is the only reactant because this H2 doesn't want to react with anything. It's neutral, it's inert. So this H negative here is going to react as this molecule's own base. It's going to react as its own nucleophile. It's going to react with itself. So this nucleophile, this leaving group is going to leave. This is a very good leaving group. It's going to leave, and you get this here. One of these lone pairs is therefore going to fulfill that positive charge, making a bond. That is how you get that. Just a number. One easy way to do this is to follow your numbers. So Christy, does that make more sense? This is again, this is a much more complex. It's a multi-step problem. You're going to see it a lot in Orgo 2, and so I don't expect him to ask something like this more than once or twice. You're going to get something more straightforward like these. But I just wanted to go over this because I've seen it before on an extra credit type of question. What type would that be? So, is this primary, secondary, tertiary? Secondary, and is just a H negative strong or weak? So based on that rationale, it's going to be an SN1 reaction. But you could also argue that it's a strong nucleophile because it has a negative charge. So if there's a rule of thumb that I've come across that they kind of go over in SI, if it doesn't have a negative charge on it, it's a weak. It's a weak nucleophile. But if it does have a negative charge on it, it's a strong nucleophile. So you could kind of go either way with this. Definitely take it to one of the other leaders or OC squared or whatever. But again, it's not something to worry about. I have never seen this on an exam. I've only seen it on actual credit. But I know you guys value that, and so that's why I wanted to go over it. But that is pretty much all I have for you today. Again, if this was kind of going over your head, go over the videos that Jermaine posted. He goes over the underlying concepts in order to apply to these types of questions. I wanted to go over more problems this time because a lot of people struggle with this chapter. But that is all I have for you guys. Hopefully these problems, because these have occurred in bonding before, hopefully it was a good intro into what you may or may not see. I'm going to stay back for a few minutes, but that is all I have for you guys.